So the last thing we need to talk about is just ways to make the truth tables a little bit quicker. So as you can see, the more letters you keep adding to your argument, the more statements that are within your argument, the longer and more complicated the truth table gets. Now there's an easier way of using truth tables to determine validity or invalidity, kind of a shortcut way, and we refer to these as indirect truth tables. So the way that these essentially work is, again, what we're trying to do with all truth tables is we're trying to get it where we're trying to look for a case in which all the premises are true and the conclusion is false. So the idea behind indirect truth tables is that we're going to just try to force that to be the case. So we're going to try to make it. We're going to say, okay, so let's assume that the conclusion is false. Can we make the premises true? And so essentially what we're going to do with indirect truth tables is sort of work backwards. All right. So once again here, we're going to kind of lay our argument out on the table sort of way of doing things. But this time we're not going to have, or you don't really need a column for each letter. You can just simply put them off to the side like so. Okay. Okay. So again, we're going to have a little column here for the first premise, which is A or not B, horseshoe, therefore C. All right. And then we have another column for our second premise, not C. And then again, we have our conclusion here of tilde, not A or not B. Okay? So once again, as we did with the truth functions and the truth tables, we want to locate the main operator in each one of these statements. Okay? So obviously, the middle one here, the second premise is pretty easy. There's only one operator, and so that's going to be the tilde. That's going to be your main operator. Okay, but if we're looking over here at the conclusion, then we need to figure out, we have three different operators, and we need to figure out which one has the widest range. Well, so the tilde here, this second tilde here, is only applying to B, so that's going to be the one with the shortest range. And the wedge here applies to the A and the not B, so that's going to be our second one. So the main operator, or the operator with the widest range here, is the tilde that's out in front of this whole disjunction. Alright? So that's going to be our third step, and it's the main operator. Over here, we have, again, a case in which then there's a not B, so we can automatically assume, since that's only negating the B, that that's going to be our first step. We have a wedge again. That one is only covering A and then not B, so it's going to be our second one. And so the operator with the widest range here, it's including everything, is of course our horseshoe. Okay? And so the way these truncated indirect truth tables work is that we want to make the main operator in this column here, the conclusion column operator, the conclusion column, excuse me, we want to make the tilde false. So we're automatically setting the final value to false. And then we're going to proceed to work backwards. Okay then. So the way it works here is that that we want our second operator here, the wedge, we want it to be true, because obviously the opposite of true is going to be false. Right? Well, there are a wide variety, since this is a disjunction, we know that there are at least three different ways in which a disjunction can be true. Both disjuncts can be true, or one or the other one can be false. But they can't both be false. So we kind of don't have a lot of information to go with so far yet on this one, because we could, plug in all sorts of values. So let's just kind of go over here for a second, like put this one on pause, and go over to our second premise here of not C. So again, we want our premises to be true and our conclusion false, so we want this premise and its final values, and its final valuation, I should say. We want it to be true. So we want tilde C to be true. Well, obviously, if everything under the tilde has the value of true, then the C initially had to be false. Okay. So we can go ahead. We're kind of like putting together the pieces of the puzzle here. So we automatically we're locked into saying that C has to be false. So let's just go ahead and plug in that value wherever we find the letter C. All right. So here we have C, and it's false. And we know, okay, so then this C is to the right of the horseshoe, and we know, thinking back to our operator tables, that if a conditional has a false consequent and a true antecedent, then the whole conditional, is going to be false. And we don't want that, right? Because again, the main operator here is the horseshoe, and we want that horseshoe to be true, ultimately, because we want the whole value of the premise to be true. So we don't want whatever's to the left of the horseshoe to be true. We want it to be false, ultimately. So we want to make this wedge here a false statement. All right. Okay. So how would we make a disjunction false? Well, both sides, both disjuncts would have to be false. So in this case, A would have to be false, so there's our value for A. And in this case, not B would have to be false, okay? Because, again, the initial value of B would have to be true and then made into the opposite by the tilde. So B is going to have to be true initially to be true, in order for this thing to be, in order for this disjunction to ultimately be false. All right, so now we have all of a sudden all of our values. So let's see. So we managed to make this premise true. We managed to make this premise true, but if we plug in these values, can we make this conclusion false? So let's see. So we plug in A, or F for A, and then we say that B was true initially, but now we have our tilde, which is making it false, right? So false or false is actually not true, okay? So this obviously doesn't work. It's actually false. And so if this whole value of this disjunction is false, then if you negate it, it's not going to be false, it's going to be true. All right, so what I've shown here is that the table does not work. So when it does not work, when you cannot make it where all the premises are true and the conclusion is false, then you have proof then that this whole argument here is actually a valid argument. So it's sort of a backwards way of thinking, but if the table works, then the argument is valid, or excuse me, is invalid. But if the table does not work, then the argument is valid.